Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be applying our lessons about the quantum nature of electrons and photons that we learned from the photoelectric effect and looking actually at atoms. And it turns out there's actually a fairly similar phenomenon in in elemental species as you get in the photoelectric effect. So what happens is you can heat any of your given elemental species in their pure elemental form. And what ends up happening is we get very discrete wavelengths of light out. And again, this isn't like the black body radiation where you get a big broad spectrum of emission across a number of wavelengths. We get very discrete quantized energies of light out. And what this really helps show is that when we're looking at elemental species, electrons move in between discrete energy levels. So there's only very specific energy differences in between these various levels that are actually allowed. And we can have light emitted at these very specific points and no other. So the logical explanation for how we get these discrete energy levels is that we have the electrons moving around the nucleus at very specific energy levels. And this is often called the Bohr model, but you may know it as the planetary model, where I can have an electron moving very close to the nucleus or slightly further away or even further out, where n represents essentially which orbit the electron is moving around the nucleus. And it turns out this is actually a pretty decent explanation of fairly simple elements, also known as hydrogenic models, atoms, because we have a single electron, just like for hydrogen. However, the charge can range from, say, hydrogen, which has one electron, one proton, helium plus, which has two protons and one electron, lithium 2 plus, three protons, one electron, all the way through the periodic table. However, not too surprisingly, as we get to heavier elements, we're a little less likely to see that in nature. But they're a pretty good way to start with electronic behavior because I only have one electron to model. And the energies of these hydrogenic systems can actually be fairly well modeled by what's called the Rydberg equation, where the energy of an electron moving around the nucleus can be given as negative, because a negative energy means that it's favorable. It doesn't want to leave. I have to put in energy to make it leave. So negative, the Rydberg constant, which can be given on the order of 10 times negative 18 joules. If not, this number does seem pretty small. The reason why is because this is the energy of an individual molecule or atom. If you want to go ahead and scale it up to macroscopic levels, multiply it by Avogadro's constant, which by the way is 10 to the 23rd, to get it on a molar basis. And you'll find that this is actually a fairly big number in that sense. And then it's divided by the energy level. So where n is going to be our energy level. So what we find is that the electron will be most happy at a low energy level and decreasingly happy the further out I go. And using this Rydberg equation, what we can show is that the further away I move from the nucleus, the more the energy levels become tightly packed. Because again, as I move fairly far away, I'm already far away from my nucleus. What's a little bit further? And we can look at this kind of quantitatively. So at the first energy level, so the closest it can become, I have an energy of the negative of the Rydberg. Then I lose 0.75, I lose 3/4 of that when I go up to the second energy level. So this is a big loss going from 1 to 2. So these are very widely separated energy levels. When I go from 2 to 3, well, okay, it goes down by half again. But compared to this first step, that's not that much. And as I go from 3 to 4, each time the energy difference is a little bit less as they eventually converge so that it barely changes when I'm far out. And so again, what we find is that it'll take a lot of energy to make an electron move out of that ground state. But again, the further out I go, the less energy it takes to make the electron move. And again, this is all looking at the hydrogen atom. And so we can find is that we can specifically figure out the energy required to move an electron between these orbitals if I use the Rydberg constant and the difference of 1 over my initial energy level minus 1 over my final energy level, both these energy levels squared. Now, again, the reason why we have this squared is because it showed up in our Rydberg equation. Now, the reason why we're having initial minus final is that if we think about it, if I have a very stable system and I go higher energy, this should require a positive energy difference. 1 over 1, that's going to be 1. 1 over anything bigger is going to be a smaller number. So that means that this will, as I go from low to high, this will always be a positive number, meaning it's always going to require energy for this transition. However, in reality, what we often have is we go ahead and, as I said at the beginning, we heat up this nucleus. We put a whole bunch of energy into our element. So this can be through heat or light or lasers or any number of sources. But let's say I heat it up, I get it to a high energy level, and then I let it relax, and this should release light. So what can happen is I can release light as I go from the n equals 5 to the n equals 2 energy level. And so again, this should be, the first number should be smaller than my second number, meaning I'm going to have a release of energy. Now, when we do the math, we find out that this is about 0.2 Rydbergs, which if we use our Rydberg energy is about negative 4.6 times 10 to the negative 19th joules. So this feels pretty low, but let's go ahead and turn this what it is in terms of a wavelength of light. So if we go back and look at our examinations of light, what we find is that this translates to about 434 nanometers. In other words, this is going to be blue light. So if you take a look at the hydrogen spectrum, there should be a blue light moment. If we're moving from a lower energy level, this means that all such as n to the 4th, there should be a lower energy difference in between the 2 and 4 or the 2 and 3. And so these would be more what we call redshifted. Higher wavelengths, lower energy, move more towards the red spectrum. As I go further and further out, it's going to become higher and higher energy, or more what we call blue shifted, as it becomes closer to these lower wavelengths, higher energy systems. So let's go ahead and look at these energy differences in kind of a different way. So what often happens is we can go ahead and excite a system either by putting in light, such as a laser, or heating the system, and we bring it to a very high energy state. So occasionally here it can decay, but most of the time we go ahead and drop back down to that low energy level because molecules like to be in low energy states. A good way to think about it is atoms are a lot like people. They like to be as lazy as possible and move down. They don't want to go anywhere. However, when it relaxes down, it's going to emit a photon because that energy that it's losing has to go somewhere. So released as a photon. So because it's hot, it needs to get away from that extra movement, climbs up, and then as it drops down, it drops down a ladder, it goes ahead and releases energy. And what we're doing is we're measuring this emitted light. Now, in practice, what we do is we'll take something like a helium lamp or a hydrogen lamp. We'll go ahead and heat it up. And this is actually where neon lights come from. You'll take a neon, a noble gas, heat it up, move it up in these energy levels. And then as the atom relaxes, it emits the light. And one of the cool things you can do is, first of all, send the light through a slit to get a narrow beam, put it through a prism. And what ends up happening is the higher wavelength light is going to run into more molecules along the way, and it's going to move a little bit slower and be moved down along the prism. And the higher wavelength light will make more of a straight line path and be less deflected. And this is originally how you could determine the different spectrum of light is by going through a prism. You see something very similar when light from the sun hits water droplets. The water droplets act as a prism, and that's how we get a rainbow, because the sun emits a continuum of light spectra. If you did the same thing for neon light, you get very specific wavelengths if you saw them at all, because again, each individual spectrum may not be intense enough. And again, what we tend to find is that every given atom will release a very specific set of wavelengths of light. So if I'm looking at hydrogen, what we have is called a Balmer series, showing up in the visible light spectrum, where we can have a relaxation from the n equals 6 to the n equals 2, n equals 5 to the n equals 2, which we did the math for, n equals 4 to n equals 2, and n equals 3 to n equals 2. Each will have a slightly different color and be very distinguished. If I try and relax into the n equals 1, well, it turns out the energy differences are very high, so I have very low wavelengths, so we won't see those. When we go to the when we relax into the n equals 3 or n equals 4, well, the energy differences are so low that they're often a little too high of a wavelength, a little too low energy for us to see. So this dropping to the n equals 2 is usually the one that people like talking about because we can physically see it. Now, this helps tell the difference in between individual energy levels. However, you can use the same Rydberg model to look specifically at the energy of each of these various orbits. Because the classic way we can look at this is using something called the ionization energy. So this is going to be the energy it takes to completely remove an electron from the nucleus. So a good way to think about this is if I'm releasing an electron from the n equals 1 state, it's going to be the energy it takes to go from the n equals 1 to the n equals infinity, where the electron is infinitely away from the nucleus. And we can use the Rydberg equation for this. Now, when we do this, our initial state is going to be whatever orbit we're looking at. However, our final state is going to be that infinite, and 1 over infinity is 0. So we can simplify this equation as the ionization energy for a hydrogen atom will be the Rydberg energy divided by the squared of the energy level I'm moving an electron from. So if I'm moving an electron from the ground state, it's going to require the Rydberg energy, which, by the way, is exactly how the Rydberg energy was calculated, based on the ionization energy of a hydrogen atom, which is, again, the Rydberg energy. However, all of our equations so far only really addressed hydrogen. However, a lot of times we're interested in other atoms. So for the greater spectrum of hydrogenic atoms, we have to deal with the fact that the nucleus has greater charge. So the electrons are going to be much more reluctant to move away from the nucleus. So we can model this by essentially increasing the difficulty of the electron from moving away by including this z squared term, where z is the atomic number, or another way of looking at it, the charge of the nucleus. The more charged the nucleus, the more the electron wants to be near the nucleus. And again, this model does assume we only have a single electron, so our hydrogenic systems. Otherwise, most of our equations are going to operate just the same way. Just tag in a z squared next to the Rydberg constant to help modify the behavior. However, one of the things that is worth noting is that the Bohr model is a fairly simplistic model. Electrons don't just move in nice orbital circles or even spheres around the nucleus. They're going to be a lot more, well, messy, because electrons are inherently, just like photons, quantum mechanical properties. And it turns out that when we get to this small level, they turn to behave a little bit more like waves. They're going to spread out and interact with each other in some very distinct ways we don't often see at a macroscopic level. So we're going to dive into this wave behavior of our particles next time. See you then.